Hi everyone! Welcome back to integralcalc.com. Today we're going to be doing another second order non-homogeneous differential equations problem. And in this particular problem we've been given the equation y double prime plus 2y prime equals 24x plus e to the negative 2x. The thing that makes this equation non-homogeneous is the fact that the right hand side, 24x plus e to the negative 2x, is not equal to 0. When you have a second order differential equation and it's equal to 0, you have 0 on the right hand side, it's a homogeneous differential equation. Anything not equal to 0 is a non-homogeneous differential equation, so clearly ours is non-homogeneous. I would also say that these here, y double prime, indicates the second derivative of y prime indicates the first derivative of y. So we're going to go through how to solve for both the general and particular solutions of this non-homogeneous differential equation. And the way we're going to do it is first by ignoring completely the right-hand side of our equation. So we're going to pretend essentially that we have a homogeneous differential equation that's equal to 0, and we're going to ignore entirely this 24x plus e to the negative 2x. So we'll convert the left-hand side to something a little bit simpler. The way I like to do this with differential equations is second order differential equations is to count the number of hash marks here on this y variable. Notice that there's 2. So because there's 2, this becomes r squared. Y double prime becomes r squared. Here there's 1 hash mark, so y prime becomes r to the first power, or just r. So we have plus 2r, and we're going to set this equal to 0 because again we're ignoring the right hand side. Now we want to go ahead and solve for r, so we'll factor out an r and get r times r plus 2 equals 0. Solving for r, we find that r is equal to either 0 or negative 2. So depending on what you find here, in this particular case we have distinct real roots because we have 2 solutions for r. They are real numbers and they're different from one another, so they're distinct real roots. You can also have equal real roots where you have 2 roots that are the same. That would be like if you had r plus 2 times r plus 2 equal to 0, and so you had 2 roots but they were both equal to negative 2. That would be equal real roots. You can also have complex conjugate roots, and each of these different scenarios mean that you're going to use a different formula. In this case we have distinct real roots, which means we're going to be using this formula here for y of x, where the roots are represented by r sub 1 and r sub 2. So we'll go ahead and plug those into our formula for y of x, and this y of x here is going to give us the general solution of this differential equation. So our general solution is c sub 1 e to the 0x plus c sub 2 e to the negative 2x. Of course we can simplify this because in the first term we have e to the 0x. 0 times x becomes 0, and e to the 0, or anything raised to the 0 power, is just 1. So 1 times c sub 1, of course, just gives us c sub 1. And then we have plus c sub 2 e to the negative 2x. So we've simplified it. This is now the general solution to our differential equation. So we've got the general solution, but what we really want to find is the particular solution based on what we've been given over here in the right-hand side of our original equation. So there's a couple different methods that you can use to solve for the particular solution of a non-homogeneous differential equation. The one we're going to be using is the simplest method, which is called the method of undetermined coefficients. And when we use undetermined coefficients, the first thing we need to do is make a guess about what the format of the right-hand side is. And I know it probably sounds weird to say we're going to make a guess. Really, you want to just build this out by using the most logical format you can imagine for the right-hand side, and then making adjustments to your guess depending on what your results are. And it's just going to take a little bit of practice, but you'll get an idea for what I mean. So we're gonna denote the particular solution as y sub p, and right now I'm just going to come up with my best guess about the format of the right-hand side. And what you usually end up doing is a couple things that you can do right off the bat. First of all, replacing constants or constant numbers with variables. So for example, this 24 here, we're going to replace with a variable a. You don't want to replace numbers that are either inside the exponent of the number e, so this -2 here we're going to go ahead and leave alone. Also, if you have a number inside of a trigonometric identity, so for example sine of 2x, you wouldn't want to replace that 2 with a variable. So we're going to leave those kinds of things alone. But this 24 here we're going to replace with the variable a. The other thing too that you want to be aware of is there's a couple different formats that the right-hand side of your non-homogeneous differential equation can come in. What you'll see most often, and let me just draw an arrow over here, what you'll see most often are polynomials, and the 24x of our right-hand side is part of a polynomial. You'll also see things with the number e, so we also have e to the -2x on ours, so we have a combination. And then you'll see trigonometric identities, like for example sine of 2x, and these things might be combined, but this is what you're going to see most often. In this case, we've got part of a polynomial and we also have something that involves the number e, so we're kind of going to treat those things separately. We're going to deal with the 24x separately from the e to the -2x. When you've got a polynomial, you have to include with variables everything that's on your right-hand side plus all lower degrees of the polynomial. So for example, you know when you have a polynomial like x squared plus 2x plus 2 or something like that, if that were our right-hand side, we would want to replace this with ax squared plus bx plus c to account for each one of those terms. If you didn't have the 2 over here on the right-hand side and you just had x squared plus 2x, you would still need to include the c here because it's a lower degree than the x squared and the 2x, right? You have x squared, you have x to the first power, and then you have x to the 0 power when you have a constant. You need to include each one of those. So even if we were only given x squared, you would still need to include ax squared plus bx plus c. So in this case, we're given 24x. We still need to include the essentially bx for the 24x and the c. We need to include something for the constant. Both of those things need to be included in our particular solution. So for 24x, we're going to go ahead and say a to the x, but then we're also going to add in b for the constant. So that'll be what we'll use for our polynomial. Then for the e to the -2x, we can just go ahead and say plus c e to the -2x. We want to go ahead and put that constant in front of it. So this is a fairly decent first guess for what the right-hand side might look like. But we need to make a couple adjustments, and the reason is because we have some things that are going to be overlapping with our general solution. And I know this is confusing, but again, it just takes a little bit of practice, and you'll get better at seeing how to put together a guess for the particular solution. But the things that we need to be aware of are if we look at this general solution here and we look at our particular solution, our guess for the particular solution, we have a constant here, b, and a constant c plus 1. Those things aren't different from one another at all. They're both constants, and we can't have that. So since we have constants overlapping here, what we need to do to eliminate that overlap is multiply the polynomial part of our particular solution by x. So we're going to multiply ax plus b times x, which is going to give us a bx here, and an ax squared is what that's going to turn into. And now bx no longer overlaps with this constant c, right? When it was just b and c sub 1, those two things were constants. Now bx is distinctly different from just the constant c sub 1. So we've taken care of the polynomial part. We also have some overlap with this c sub 2 e to the -2x and c e to the -2x in the particular solution. Those things aren't different from one another either. They also overlap because c sub 2 and c both represent a constant, and therefore these things aren't different from each other at all. So in order to eliminate that overlap, what we're going to need to do is multiply this part here in the particular solution by x. So we'll have cx e to the -2x. So that's made it distinctly different. from the general solution. So whenever you have an overlap situation like that, you just need to multiply whatever it is in the particular solution that's overlapping by x to eliminate the overlap. We did it for the polynomial portion, ax plus b, and we also did it for the portion that involved the number e here. So now we've got an even better guess for the particular solution, and this is what we'll stick with. What we're going to do with the particular solution is take the first derivative of the particular solution and the second derivative of the particular solution and plug in the second derivative for y double prime of x in our original problem, and plug in the first derivative for y prime of x in our y prime in our original equation. So let's go ahead and take the derivative, the first derivative of the particular solution as we found it here. So to take the first derivative, again, we'll treat a, b, and c as constants. So to take the derivative, we'll get 2ax plus b. And then here, for cx e to the negative 2x, we'll need to use the product rule. We'll treat one function as cx and the other function as e to the negative 2x. And when we take the derivative of that using product rule, we'll get c e to the negative 2x and then minus 2cx e to the negative 2x. So that will be our first derivative, and then we're also going to need to take our second derivative, y double prime of p. And when we do that, we'll just get 2a. The b will go away completely, and then we'll get, for this c e to the negative 2x, we can take that normally. We don't need to use the product rule. So we'll get minus 2c e to the negative 2x. But again, for negative 2cx e to the negative 2x, we'll need to use product rule to take the derivative, and we'll get minus 2c e to the negative 2x, and then it would be plus 4cx e to the negative 2x. And that would be our second derivative. So now that we have the first and second derivative, we can plug the second derivative in for y double prime and the first derivative in for y prime into our original equation. I'm going to go ahead and erase everything over here so that we can have some space. So, like I said, we're going to plug everything in to the left-hand side of our equation. We're going to leave the right-hand side alone. So plugging in the first derivative, plugging in the second derivative here for, let me erase this so we can use it. Plugging that second derivative in for y double prime, we'll get 2a minus 2c e to the negative 2x minus 2c e to the negative 2x plus 4cx e to the negative 2x. And then we'll plug in, we'll say, I'm going to do this, I don't know if I'll fit, let's see if I can fit it, plus 2 times the first derivative. So now we'll take the first derivative of the particular solution and we'll plug it in for y prime here. Obviously we've got this 2 multiplied out in front. So 2 times 2ax plus b plus c e to the negative 2x minus 2cx e to the negative 2x. And then we're going to set that equal to, let me erase this, we'll set that equal to the right-hand side, which we're going to leave completely alone. So it's going to be equal to 24x plus e to the negative 2x. And now what we want to do is go ahead and simplify the right-hand side, the left-hand side as much as we can. So we'll end up with, instead of this part over here, I'm going to multiply out this 2 so we can see. We'll end up with 4ax plus 2b plus 2c e to the negative 2x minus 4cx e to the negative 2x. So now we can, for everything here above this line, we're going to want to go ahead and combine terms as much as we can. And this part is all crossed out now. So we want to go ahead and combine terms as much as we can. So let's see, we'll start with, what are we going to start with? Well, we've got 2a plus 2b, right? Those are constants, so there's 2a and 2b. And then we have a minus 2c e to the negative 2x. Minus 2c e to the negative 2x is going to be minus 4c e to the negative 2x. And over here we have a plus 2c e to the negative 2x. So we're back to minus 2c e to the negative 2x for those three terms. Then we have plus 4cx e to the negative 2x minus 4cx e to the negative 2x. So these are going to completely cancel. And the only other thing we have is plus 4ax equals 24x plus e to the negative 2x. So now we want to use the method, remember we said we were going to use the method of undetermined coefficients to find the particular solution. Well, we have coefficients here on the left and right hand sides that we need to go ahead and match up. So what we mean by that is we have, for example, 4a over here on the left hand side and 24 over here on the right hand side. They are both coefficients on the x variable here. So that means that they have to be equal to one another. So we're going to go ahead and say 4a equals 24. We also know that we have negative 2c as a coefficient on this e to the negative 2x, and over here we've got a coefficient essentially of 1 on the e to the negative 2x. So we know that negative 2c must be equal to 1. And then we also know that we have this coefficient here, 2a plus 2b, and we have a constant over here of 0, right? We have a constant over here on the right hand side of 0. We have a constant of 2a plus 2b, right, where there's no x variable involved, over here on the left. So we know that 2a plus 2b must be equal to 0. And now we have a series of simultaneous equations that we can solve for a, b, and c. So if we divide both sides of this first equation by 4, we'll find that a is equal to 6. If we divide both sides of this equation by negative 2, we'll find that c is equal to negative 1/2. And then if we plug a equals 6 into our third equation, we'll get 2 times 6 plus 2b equals 0. And then that gives us 12 plus 2b equals 0. If we subtract 12 from both sides, we'll get 2b equals negative 12, and then dividing both sides by 2, we find that b is equal to negative 6. So these are now our three coefficients, a, b, and c. So now we can plug these coefficients. That's what we do to go through the process of undetermined coefficients. Now that we have the coefficients, we can plug them into our particular solution over here that we found originally. And when you use the method of undetermined coefficients, it's worth noting that as long as you can solve for the coefficients, you know that you've done the problem correctly. If you find something that is impossible, for example, if you were to end up with something, like 0 equals 6, which is obviously impossible, or something that doesn't make sense, then you know that the method of undetermined coefficients either doesn't work and you need to use a different method, or that your particular solution was wrong and you need to go back and adjust your particular solution. In this case, since we successfully found values of a, b, and c, we know that it worked. So now we can say, and I don't need these anymore, so let me just give myself a little more room because we're almost done. So now we know that the particular solution, y sub p, we're going to go ahead and plug in a, b, and c, is equal to 6x squared. We found that b was equal to negative 6, so we'll get minus 6x, and we found that c was equal to negative 1/2, so minus 1/2 x e to the negative 2x. So that's our particular solution, but in order to find the final answer for the particular solution, what we actually need to do is add the general and particular solutions together. So these two right here. We're going to be adding these two together. So what we end up with is, and you always want to state the general solution first, so we have y of x equals c sub 1 plus c sub 2 e to the negative 2x. That's the general solution part. And then we're going to add to that the particular solution. 6x squared minus 6x minus 1/2 x e to the negative 2x. And that right there is our final answer for the particular solution of this second order differential equation. So I know it was a lot of steps. I think the most difficult part is remembering how to get through the problem and how to make a guess for the particular solution. But I'll do several more videos, and we'll get to go through making guesses together. So I hope that video helped you guys, and I will see you in the next one.